My bona fide students not to be. Welcome to the continuation of our class in physics. We still have 2 more lessons to go, if I'm not mistaken, either 2 or 3 more lessons to go. And we are looking at graphical interpretation, distance time graph, and velocity time graph. Those are the 2 most important and also the 2 most common graphs that we always interpret in physics. Okay, commonly set in College of Nursing Sciences entrance exam. All right. So when you hear a distance time graph or a velocity time graph, it means that you plot for distance time graph. Distance is plotted against time. All right. Against time. For velocity time graph, velocity is plotted against what? Time. Okay. So the distance time graph is used to know the distance covered within a specific amount of time. The velocity time graph is used to note the velocity reached within a specific amount of time. Now let's look at the interpretation of both. Taking distance time graph as the first, this is the graph. Remember, since we are plotting one against the other, which we are plotting distance against time, we put distance on the y-axis and time on the s-axis. So we put our time here, we put our distance here. All right. Remember, what we are looking is graphical interpretation. All right. So for the distance time graph, here is distance, here is time. So let me just put something random. Okay, here is from the point of rest. Okay, then we have something like this. We have something like this. Okay, let me just put 1. Then we have something like this. All right. Here is the point at which it goes back to what? To rest. All right. So this is a distance time graph. All right. So plotting the distance time graph, let me just make this a little bit straight. All right. So interpreting the distance time graph, what do? How do we interpret? Don't know what is wrong with my marker. How do we interpret? It's very easy. Okay. The distance time in the distance time graph, the slope of the graph is usually known as the speed. All these are slope. Anywhere you just see diagonal like this is slope. This one is slope. All right. All right. This one is also slope. This one is also slope. So all these slopes are speed. All right. In a distance time graph, they are called speed. Always look at the graph. Is it distance time graph or is it velocity time graph? All these are slopes. They are known as speed. So from here to here is speed. From here to here is speed. From here to here is speed. From here to here is also a slope. All right. It's also what? Speed. All right. So that is the first interpretation of the distance time graph. So here that has a straight line like this, horizontal straight like this. This place is a constant speed. All right. The speed is not changing. Here you can see that it's ascending. The speed is changing. It's lower here, higher here, higher here, higher here, higher here, lower here, higher here, higher here, and so on and so forth. So this is a constant speed. All right. Nothing changed there. All right. So for the second interpretation, the straight line is known as what? The constant speed or the uniform speed. We already talked about that. And this curve is known as the acceleration. So from here, like this curve like this is known as what? The what? Acceleration. All right. So slope is equal to speed. The curve is equal to acceleration. All right. What are we noting again? Okay, the straight line is what? Straight line is either constant, can call it constant, or uniform speed. All right. Straight line can be called either constant or uniform speed. All right, speed. As easy as that. So that's that for distance time graph. Let's now look at velocity time graph. Okay. Very easy to interpret. We are going to see the little difference between the distance time graph and the velocity time graph. All right. So for the velocity time graph, we plot velocity against time. All right. We plot velocity against time. Here, we are now going to have velocity on the y-axis. Then we have time on the what? S-axis. All right. So we plot this like this. All right. Here's the point of rest. Let's say we take something like this. We take another one like this, like this, like this. All right. So this velocity time graph, you can actually use this velocity time graph to solve a lot of questions related to motion. All right. If you know how to use this velocity time graph, it's very easy. Just use the figure provided, or you can draw the graph yourself from the parameters given in the question. But sometimes, especially when you don't know how to use it, it's a waste of time if you don't know how to use it. But if you know how to use it, it's not a waste of time. But there's also some exam questions you can come across, and you are going to see velocity time graph, and they will ask you to make some calculations through the velocity time graph. All right. So we are going to understand some of this now. So for a velocity time graph, it says that the slope is equal to what? Is the acceleration. All right. Is the acceleration. Remember, the curve in a distance time graph, that's what is the acceleration. But here, the slope is the acceleration. And what is slope? All these diagonals. All right. All these places are slope. Slope, slope, slope. Here, this flat place is the constant speed. The straight line or horizontal line, this straight part is equal to what? Constant speed. All right. Constant speed. All right. So let's see if I'm forgetting any other thing. So this is constant speed. This is slope. Then the distance covered towards a specific direction. Remember what I taught you on displacement. From here to here, the total distance, all right, distance covered is equal to what? The displacement. All right, total distance covered equal to the displacement. As easy as that. A, B, C, D. All right, so from here to here. So if you are told to solve the displacement, here is 0, rest. Let's say what we have here as displacement is, let's say 30, for example. All right, so let's say we have 30 here as displacement. So the displacement will be what? 30. Figuring out the displacement. If they ask you what is the speed from here to here, remember the SI unit of speed and velocity is what? Equally the same. All right, so this one, remember we have time here, and this one we have velocity here. So meter per second. So around here, this point is you pick the value here, then you pick the time value here, you divide. All right, let's say we have 30 here. Let's say we have here, we have 10. All right, so to calculate the speed from here to here, what are you going to do? 30 over 10 equal to 3 meter per second. That's the speed from here to here. So that's that for that. We are just making assumption, all right, to get meter per second. All right, that's that for that. So we are done with the graph interpretation for velocity time graph and distance time graph. All right. Velocity time graph and distance time graph. Velocity time graph and what? Distance time graph. So there's something about this velocity time graph that is different from distance time graph. Remember, in the distance time graph, the straight line, that is the what? The constant speed, right? Or the uniform speed in the distance time graph. But for the velocity time graph, this one, this slope is the acceleration. All right. That's that for that. All right. Then this one, anywhere you just see a straight line, just know it's constant speed. Or it can also be called uniform speed. All right. So let's move over to the next topic. All right. Our next topic here is projectile. All right. This projectile, we are going to be very, very fast with it. Projectile is a very interesting topic. I love projectile so much. I am going to make you understand projectile today. Okay. If you've never understood projectile, I'm going to make you understand projectile. Also, you can answer so many questions on projectile using the equation of motion. Those 3 equations of motion. You can use that equation to answer many questions from projectile, numerous questions. I can't lie to you. You can use it. Okay. Provided the parameter you are using is there. All right. Or the parameter that you ought to use. So we have projectile. All right. Projectile. This is an object. Okay. An object is known as projectile. Then projectile motion is a motion of a projectile. All right. But firstly, we have to understand what a projectile is. All right. So let's put a person here. Let's say this is Ronaldo. This is Ronaldo's leg. All right. This is a ball. So let's draw something here. All right. So this is the ball. 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 And this is the ball at rest. So here, the ball is at rest. Here, the ball is also at rest. All right. Okay. So, like we said, a projectile is an object that is fired into space. Okay. That's what, when after you fire the object into space or thrown into space, the object forms a curve motion like this. All right, you see it forms a curve motion. You throw it like this, it forms a curve motion just like this. This ball is fired into space by Ronaldo, is played into space by Ronaldo. The ball goes up and creates a curve motion. This curve motion here is called projectile motion, as simple as ABCD. All right, so this projectile motion is as a result of what? Gravitational pull. As simple as that. As a result of gravitational pull. Provided there is no air resistance, no air disturbing the projectile thrown into space, it must create this projectile motion. Now, let's understand why this projectile motion occurs, or what is behind the mechanism behind this projectile motion. First of all, we have to understand what is called angular velocity. All right. This is the symbol. Angular velocity. We have to understand what it is. Angular velocity is velocity, the normal velocity we know, but it's a velocity that creates an angle. The velocity is determined by an angle. That's why it's called angular velocity. It moves in an angle. It is created in an angle. What is angle? Our normal geometry now, that's angle, right? So as angle continues to change, all right, angular velocity occurs as a result of a change in angle. So change in what? Angle brings about angular velocity due to what? Change in angle. I will give you an example. It's very important in this projectile motion. So let's say when Ronaldo fires this ball, the ball moved at what? Let's say at 20 Newton. That was the force applied to the ball. And let's say the force created a velocity of, let's say, 40 meter per second. All right, this is the velocity. Okay, the velocity. So let's say the gravitational pull is 10 meter per second. All right, per second squared. This is what? Gravitational pull, acceleration due to gravity. All right. So this gravitational pull is what the earth used in pulling an object. It pulls the object downwards. All right. So when this Ronaldo fires the ball moves. Okay. It moves, it ascends slowly because of the force, and the force generates this velocity. So as it accelerates, as it goes up, the force begins to what? Reduce, because it's not a constant force. You just kick the ball and allow the ball to what? Move into space. All right. So as the ball continues to accelerate, the force reduces. As the force reduces, the velocity reduces. It gets to a point, this velocity is going to be equal to 10 meters per second. All right. It's going to be equal to this acceleration due to gravity. All right. So that point is at the highest height that it can attain. That's here. It cannot accelerate at this point again, because the velocity is already equal to what? This. So it gets to a point, the velocity continues to reduce. Okay, it reduce, and this one will now be greater than the velocity. So 10 meters per second acceleration due to gravity, the gravitational pull is now greater than the velocity. So what happens in turn? The gravitational pull of the earth now starts acting on the ball, okay, on the object. The object now starts what? Decelerating, falling down. The object starts dropping gradually, because the greater this one passes the velocity, the faster the object drops from space. So it is this, that's why you see this dropping gradually until it goes back to rest at what? 0 meters per second. Okay, that's it. So this part created here is a projectile motion, and it occurs as a result of angular velocity. What is the angular velocity? This is an angle. This thing here is an angle, right angle. Okay, created by what? By the object fired into space. So because of the reduction in the force and the velocity, it changes angle. The angle at this point is not the same as the angle at this point. You can see that the angle is changing. See another angle. When the ball was at the middle here, it was at angle 90. Can you see? See another angle here again. Okay, that's how the angle continues to change. So for projectile motion to be created, there must be angular velocity. So this one is an angle, this is another angle, this is another angle. Okay, you can see. It's not supposed to be like this. So let me draw the angle. Let me indicate the angle properly, because all these I'm just doing here, I'm just putting everything as angle 90. All right, this is how it's supposed to be. This is how it should be. All right, the first angle should come from here. Okay, what angle is this? It's a very low angle. See another angle again. This one is angle 45. This one is maybe angle is more than 45. Maybe let's put it 60. Angle 60. Here is angle 90. Can you see the change of angle? Okay, as the ball ascends and descends, or as the object, the projectile fired into space, ascend and descend. that is what brings about projectile motion. That's called angular velocity. As simple as that. Projectile is very easy. So now we are going to look at the, the application of projectile. All right, application of projectile. Projectile is applied in sport, like in football, like the example we just did. Another one in basketball, where you drop ball. Okay, another one again is in rocket launchers. All right, rocket launchers, volleyball, ballistic and missiles. All right, water fountain. Okay, whereby you have water like this. You have water. Let's say this is the place. Then water fountains like this. This is water fountain, projectile. You can see the curved motion. All right. The water fountain test is done with what gas? Let me quickly teach us this. I just remembered. It's usually done with sulfur oxide gas. Okay. But they can also ask you a question. Say, apart from sulfur oxide gas, which other gas can we use to carry out the water fountain test? Okay. We can also use ammonia. All right. We can use ammonia to carry that test out too. Okay. So take note of that. Now, let's quickly look at the formulas of projectile. The formulas we use in projectile. Okay. Or the equations in projectile calculation. They are very easy. Remember, I told you that if you know the 3 laws of equation, you can easily get, you can easily use it to solve any question relating to motion. All right, provided you know the 3 equations, you know how to use them, and you understand vector, just like I've taught you vector. Remember, I said when you have a vertical inclination, you use sine. Horizontal inclination, horizontal angle, you use cos. All right, to solve. So you are going to equate everything into your law of motion. That's if you are using an indirect, approach. But using the formulas provided for the solving of projectile is a direct approach. So the first one we are going to look at here is time of flight. So the time of flight of a projectile is equal to, is usually written as capital letter T. Okay, that's the time of flight of a projectile. Is equal to 2u sine theta over g. All right, where g equal to what? Acceleration due to gravity. Due to gravity. U is equal to initial velocity. Initial v. While sine theta is the angle. Theta is the angle. Theta equal to angle. Okay, angle. G, we already talked about that. So mind you, we also have time taken to reach the maximum height, small letter t, which is equal to u sine theta over g. All right, time taken to reach the maximum height. That is the formula. So we also have another one, maximum height of a projectile. Maximum height. All right, just put here the mass. That's maximum height of a projectile is equal to u square sine, okay, sine theta square or sine square theta over 2g. So you can also write this as sine theta square. Okay, you can remove this one and put it here. Okay, sine theta square over 2g. Okay, that's 2 times g. All right, which other one do we have? We have range. Range of a projectile, which is equal to, it has a long formula and a short formula. We are going to do a long formula. It's usually represented in r. So the long formula is u square sine 2 theta over g. All right, then the shorter formula is when an angle is not provided. So you cancel out this. You cancel out the sine and the theta. So we are now going to be left with u square over 2g. So this one is the what? The shorter formula. All right, range u square over 2g. All right. So those are the what? The most common formula for projectile motion. Now let's look at the formula for angular velocity. In angular velocity, radius is involved. Angular velocity is something like nyash like this, equal to the distance, okay, or the angle. Remember, we are working on angle over radius. R for radius, theta for angle, okay, or is it over radius or over time? Okay, theta over time. Or it can also be written as angular velocity is equal to v over radius. All right, whereby v is the velocity, r is what? Radius. Okay, so you can use any of this formula to solve for angular velocity, depending on the parameters that you were given. All right, so there's also a formula for angular acceleration. All right, we understand the formula for centripetal force. First of all, centripetal force. What is centripetal force? Centripetal force is the force that keeps a body moving around the circle, or that keeps a body moving in a circular path. For example, this is a circular part and a body is moving around this circular part. All right. So like this, the body keeps moving around the circular part. All right. Like this. So the force that enables this body to move around this circular part is known as what? Centripetal force. And the formula is given as F equal to 1 over 2 mv squared over r. All right. Is there half? So no need for the half because that's for potential energy. So it's given as mv squared over r, where r is equal to radius, m is equal to mass, v is equal to velocity. It's also given as centripetal force equal to m angular velocity r squared, right? Hope I'm correct. All right. Angular velocity square r, not r squared. Angular velocity square r. So it depends on what you are giving to solve. This is angular velocity. This is radius. This is what? The mass. It depends on what you are giving to solve with. Okay, so we have another one called centrifugal force. Centrifugal force is the force that pulls the body away from the center. So that force that acts on this body, that pulls this body away from this center, so that the body comes to the side of the circumference of the cycle, is known as centrifugal force. Okay. Okay, centrifugal force. All right. That's it. What? Its function. Pulls the body away from the center. All right. So that's that for that. Understand it. So that's what's the application of centripetal force when the earth orbits around the sun. All right. The force that enables the earth to orbit around the sun. That's it. Or the force that enables satellites to orbit around the earth. That's one of the application. All right. mv squared over r, angular velocity. All right. Let's quickly look at simple harmonic motion. Simple harmonic motion. Simple harmonic motion is a to and fro movement, or you can call it oscillation. We normally abbreviate it as SHM, simple harmonic motion. It's an oscillation of an object, or to and fro movement of an object. Okay, to and fro movement of an object. Okay, of an object whose acceleration is directly proportional to displacement and towards the main position. All right, acceleration is directly proportional to what? Displacement. And move towards what? Or directed towards mean position. Towards mean position. All right, that's simple harmonic motion. It's a to and fro movement whereby the object acceleration is directly proportional to displacement and the object is directed or moved towards the mean position. Let's say this is a pendulum, for example. Here, at the middle here, is known as the mean position. All right, this is the mean position. I already explained mean position before, but I will explain it again. Let's say the pendulum is oscillating. This is supposed to be shorter. All right, so the pendulum is oscillating. So this is a hook. All right, so the pendulum is oscillating from right to left, from right to left. So this is the mean position. The mean position is a point of zero oscillation or zero velocity. The point of 0 meter per second. Okay, at here, potential energy, kinetic energy here, at this point, kinetic energy is equal to 0. Okay, at the mean position, kinetic energy, Ke, equal to 0 at this position. So when it oscillates, when it goes back to to and fro movement, back to the to or the fro, at this place, it has the maximum kinetic energy. Maximum Ke at this point. Okay, here we have the maximum kinetic energy. Here we have the maximum kinetic energy. Here we have kinetic energy equal to what? 0, or the minimum kinetic energy. All right, at this point. Okay, so this place is the what? Is the what? Mean position, where the kinetic energy is minimal or the most minimal, or where the kinetic energy is equal to 0. So a to and fro movement whereby the displacement is equal to acceleration. What is the displacement? Displacement is the distance covered between from here, from point A towards point B. Okay, the acceleration is what? The change of rate of what? Of acceleration is change of rate of velocity. Okay, so the change of rate of velocity is equal to the what? The total distance covered within a specific direction. So that's a what? A simple harmonic motion for you, and it takes part towards the mean position. Look at it here. This is the mean position. It always oscillates like this towards the mean position. It comes back towards the mean position again. Comes back towards. So this is a what? It's a simple harmonic motion. All right. always illustrated with a what? A pendulum bob. All right. So examples of simple harmonic motion, we have already talked about the pendulum bob, small oscillation. We have vibration of a string for string instrument. We have spring mass system. Okay, just know that it involves anything that possess small or little vibration. All right. So we have time. All right. Time for one oscillation. You know that oscillation is usually measured with time, with the time taking. All right. So we have frequency here. And what is the definition of frequency? Frequency. Frequency is the number of oscillation per second. Per second. Some textbook will tell you particle vibration per second. Some textbook will tell you circle per second. So any of the definition is correct. All right. But you have to know them in case if you jam anyone for your example. And the formula is given as frequency F is equal to 1 over the time, okay, or 1 over period. So oscillation per second. All right. Oscillation per second. All right. So what is amplitude? Remember that amplitude is the maximum distance of displacement. Okay. The maximum distance of displacement is amplitude, as easy as that. Maximum distance of displacement. Let's say this is a waveform, for example, and this is amplitude. Okay, this one is one wavelength. All right, this is one wavelength. Crest and trough. All right, one circle, half circle plus half circle, one wavelength. All right, so what's amplitude? Amplitude is this distance from here to here. Okay, so the maximum distance of displacement. Here is a distance of displacement. Remember, this wave is moving towards this direction. All right, and this is a distance of displacement. Here is another distance of displacement. It covers this distance. It's moving towards this direction. Here is another distance of displacement. Here is another distance. Where is that point that it has its maximum distance of displacement? It's at the middle here that it has the maximum. Anything apart from here is reducing now. So this point of maximum distance of displacement is known as amplitude. All right, amplitude. As easy as ABCD. So let's move over to the next. And remember, we always have a mean position. All right, we always have a mean position. And here for this waveform, what do we call the mean position here now? For this waveform is at this point, okay, at this point is the mean position, okay, so at this mean position is where we have the amplitude, okay, at this position is where we have the amplitude, the mean position. All right, maximum distance of displacement from the mean position. So we have some equations under simple harmonic motion, how to find velocity, how to find, displacement, and so on and so forth. Okay. Those are, if you want to learn those formulas, just look at the lesson notes. Okay. Just look at the lesson notes. We have about 3 formulas there for simple harmonic motion. Okay. For displacement is given as x, which is the displacement, is equal to a, which is amplitude, bracket open. Is it a sine angular velocity. A sine angular velocity times time. All right. So this one will be in brackets. Angular velocity times time will be in brackets. A is amplitude, sine angular velocity. So this is the formula to determine displacement when you are giving question under simple harmonic motion. We also have velocity. When you ask to find velocity, use velocity is equal to angular velocity root. Is it a squared? Yes, a squared minus s squared. Okay, bracket close. This one is inside root. Okay, bracket close, inside root, square root of a square minus s square. Then the third one is acceleration. How do we determine acceleration under questions related to simple harmonic motion? It's just a which is acceleration, equal to what? Negative angular velocity square times displacement. Negative angular velocity square times displacement. So that's that for the formulas. All right. So you can do where to learn the formulas too. All right. You can do where to learn the formulas too. So let's go back to the explanation of energy changes where we spoke about mean position. All right. There is something that I want to clarify there. Let's clarify something there. Because they usually set question from here. So let's say this is the hook of the pendulum bob, and this is the pendulum. This is here is one of, a string position. the second extreme position. All right, it's oscillating from right to left, or from right to left. All right, so this here is the mean position, or let me just put it inside mean position. So at this mean position, potential energy is equal to here at this position, here should be the minimum potential energy, minimum. Okay, here at this point, kinetic energy equal to maximum. So here you have the kinetic energy at this mean position. It's like the center of oscillation. The mean position is usually the center of oscillation, all right, or the center of movement. That's the mean position. If I throw a blow now, if I want to throw a blow now like this, here is, I have not released the blow. Here's the extreme position. Let me put it here, extreme position. Okay, this is also an extreme position, EP. All right, let's call it EP, extreme position. All right, so at this place, my blow is in extreme position. So when I throw this blow straight like this other place is the second extreme position. All right, so half of the journey is known as mean position, and here is where I have the greatest velocity, the greatest momentum, and the greatest force at this mean position. That's why kinetic energy is maximum at the mean position. So if I land the blow at this position, it's not going to have enough effect, enough force as when I land it at this position, the center, the mean position. All right, or I now land the blow when it's here. That's when the blow landed. It's not going to have enough effect as when it's landed at the mean position, the center of it. All right, because there the kinetic energy is maximum at that point, or at this position, this mean position. All right, so at the extreme position, what do we expect here? Remember, potential energy is stored energy possessed by a body by the virtue of its position. So when a body is stationary, that energy in the body is known as what? PE, potential energy. When a body is moving, all right, that energy possessed by the body is known as kinetic energy. All right, so here, since at this point we are not going to have the minimum what? Kinetic energy will be minimum here, because here can either be the point of rest or the point of starting point or the point of rest. So kinetic energy will be equal to minimum. You notice the minimum kinetic energy here. The potential energy equal to what? Maximum. All right, remember the energy by the virtue of its position. All right, so in the system at this position, it depends on the because here is where you normally see the break. So you can say kinetic energy at this point can either be minimum or equal to 0. Okay, kinetic energy here can either be minimum or equal to 0, because here is where you have the resting. Okay, if something swings like this during oscillation of pendulum ball, you are going to notice the pause at the extreme position. Okay, so just like that. All right, so it can either be minimum or equal to 0 depending on what you see among your option. Okay, is minimum or equal to 0. But for us to get something much more specific, let's just leave it as equal to 0. All right, it is more accurate to say it's equal to 0. But if you don't see 0 there and you see minimum, you take minimum. So kinetic energy equal to 0 at extreme position. All right, so the total energy of the system is usually constant. Total energy of the entire system is usually constant because energy is not lost. All right, at this point it's converted to potential energy, at this point converted to kinetic energy, at this point potential, just like that. Okay, just like that. Resonance is referred to as the maximum amplitude. The maximum amplitude, that is what is known as what? Resonance. The maximum amplitude. Okay, remember what amplitude is. Then inside that amplitude now, the maximum amplitude attained is known as resonance. And resonance occurs when the driving force equals the natural frequency. The driving frequency. Driving frequency equals natural frequency. That's when you get resonance. All right, resonance. Remember, is the maximum amplitude. All right, don't forget this. It's a common question in College of Nursing Sciences entrance exam. All right, they ask you resonance is formed when. So the application of resonance include radio tuning. That's number 1. Tacoma. That's number 2. We have bridges and musical instruments. Bridges, musical instruments. All right. So these are the applications of resonance, where we apply resonance. All right. Remember, resonance work with frequency. Okay. Driving frequency equal to what? Natural frequency. That's when we see resonance. We already talked about the conservation of linear momentum, and we are moving straight into the second half of our physics, where we are going to talk about gravitational field and force. Gravitational field, gravitational line of force right away. Looking at gravitational field, we already talked about gravitational field when we were talking about force field. That gravitational field is an area whereby the gravitational pull is felt. Okay, the gravitational force of the earth is experienced. Okay, that's gravitational field. Now let's quickly look at the Newton's law of gravitation, or the Newton's law of universal gravitation. Newton's law of what? Universal gravitation is something that applies to the universe. Okay, the universe, it applies to the entire universe. It states that the force of attraction between two masses, okay, which is written as M1 and M2, the force of attraction between two masses is directly proportional to the product. As you bring two of them together, is directly proportional to the product of their masses. You are now going to have M1, M2. All right, and inversely proportional to the what? To the square of their distance apart. So over r squared. The distance is given as this. So if we write this, we are going to put square here. All right. He said what? The force of attraction between two masses, M1 and M2, is directly proportional to what? To the product of the masses. This is the product of the masses, and inversely proportional to the what? That's why you are seeing over here, over r squared, the square root of their distance apart. Okay, the square of their distance apart. So if we rewrite this, we are going to include the gravitational constants. So the force of attraction, F, is equal to G, which stands for the universal gravitational constant, M1, M2. That's mass 1 times mass 2 over r squared. All right? That's that for that. The root goes off. All right? So this is the Newton's universal law of gravitation. M1 stands for mass 1, M2 stands for mass 2. All right? This G stands for what? The universal gravitational constants. And the universal gravitational constant is given as what? Is given as 6.67 times 10 raised to the power 11 times 10 raised to the power minus 11. 6.67 times 10 raised to the power minus 11 Newton meter. This what I'm writing now is the unit to Newton meter square per kilogram square. So what you are seeing here is the universal gravitational constant. This one is gravitational constant, represented as capital letter G. All right. So the application of the Newton's law of gravitation, he explains planetary law, okay, or the one they call planetary law, okay, planetary law of motion, motion involving planets, also satellites orbiting around the Earth, okay. So that's that for that. All the Earthling, everything found in the Earth is explained by this universal law of gravitation. All right. So what we are looking at next here is the gravitational potential. All right. The gravitational potential is known as the work done per unit mass that bring a body from infinity to a point in the gravitational field. The work done that brings a body from infinity to a point in the gravitational field. So this is known as gravitational potential. Gravitational potential. All right. So it has a formula. It is given as V equal to minus G over R. All right. So we are going to have mass Gm over R. All right. So that's where you still have gravitational potential energy. Okay. Gravitational potential energy U is given as minus G, capital letter M over small letter m over R. So this one is gravitational potential energy. Okay, don't stress yourself too much. Just know the Newton's law of gravitation. Okay, that's the most important thing you need to know here. The Newton's law of gravitation that I explained at first. All right, this is Newton's universal law of gravitation. Know the expression: force equal to G times mass 1 and mass 2. All right, sometimes they can put it like this. They might not put mass 1 and mass 2. They might put it as big letter mass and small letter mass. They put G over R square. F is equal to this. So this one is the universal law of gravitation. All right, for Newton. Now let's diagram. We already talked about the acceleration due to gravity of the Earth. I will talk about the two. That one is 9.8 and one is 10 meter per second square. Okay, but I said the most widely acceptable is 10 meter per second square. But use what you are given in your question to solve with. If you are not giving anyone to solve it in your question, that's when you select this one and use it for your acceleration due to gravity. All right, acceleration due to gravity. So there is usually a variation in gravitational constant on the Earth's surface. Variation, a difference. All right, this happens when you go high up, what they call altitude. All right, so as you ascend, the gravitational constant, acceleration due to gravity, not this one. You know this one, this capital letter G is gravitational constant. Small letter G is acceleration due to gravity. So as altitude increase, as it increases, gravitational, this one, gravitational acceleration due to gravity decreases. All right, it increases. Okay, so this is directly proportional to this. So as altitude decreases, as this decreases, this also what decreases. As simple as that. Also with depth inside the Earth, it's also what decrease with depth. All right, with depth. As you go down below the Earth, as depth decrease, this one also what decreases. Okay, acceleration due to gravity decreases. Remember, we also have latitude. Okay, latitude less at equator due to the Earth's rotation and bulge, and so on and so forth. All right, so the acceleration due to gravity is less at the equator of the Earth. Where's the equator of the Earth? Let's say this Earth. At the center here is known as the equator of the Earth. All right, it's usually less at the equator. Acceleration due to gravity. All right, we already discussed mass, and now let's quickly look at escape velocity. Escape velocity. So escape velocity is the velocity required for a body to escape the gravitational influence of the Earth. This gravitational pull that we are talking about here. Okay, the velocity required of a body to escape that gravitational pull of the Earth is known as escape velocity. All right, escape velocity. And it has two formulas depending on what you are given to solve with. That's why you always have to look at your parameter before solving. All right, so escape velocity is given as VE. Okay, escape velocity is equal to G M, capital letter M, okay, over R. All right, 1M, sorry, 1M, which is the capital letter M, the big M, over R. The radius is put in capital letter, but normal small letter is radius, but I don't know why they use capital letter here. Then the second formula is the one that has roots. VE is equal to 2 square root of 2 times acceleration due to gravity times radius. So this one is the second formula. Okay, so depending on what you are given, maybe your question that you want to calculate something in your question, you were given this one, the mass, you were given gravitational constant of the Earth, you were given radius of the Earth. You use this formula to solve. All right, so, or in the question you were given only acceleration due to gravity, small g, then you were given radius, then you know that this one is the most suitable formula to solve with. All right, so the escape velocity of the Earth is usually 11.12 kilometer. Wait, if you are doing this in meter, okay, let's just put what we have here, kilometer per second. It was indicated in kilometer per second. Okay, 0.12 or 0.2 kilometer per second. This is the escape velocity of the Earth. All right, what is parking orbit and weightlessness? Satellite orbit where a satellite, the particular juncture where is the position of a satellite. Let me quickly clean this. Let's understand that parking orbit. Okay. The position where a satellite remains fixed relative to the Earth's surface. You have a satellite in the Earth's surface or close to the Earth's surface. That point where this satellite remains fixed, they move, is what? The parking orbit. All right. Then he sets this question well. Take note. All right. It's also known as geostationary. You can see we have stationary inside. That's fixed. Geostationary orbit. All right. Take note. All right. Then weightlessness. Weightlessness means that no weight is felt. Okay. So when an object is weightless, no weight is felt. For example, when an astronaut is in space, they feel this weightlessness. Okay. Both the satellite and the astronaut fall freely under gravity. So there is always this weightlessness. All right. That's why you are always asked that when a man is in an elevator and the elevator is ascending, okay, why does the man feel is heavier than when it's descending? This one is when the elevator is ascending, the man is inside the elevator. And this one is when the elevator is descending, the man is inside the elevator. The man is inside. So they ask you, why does the man feel weightlessness here? And here he feels what? Additional weight. It's because of gravity. All right. It's because of what? Gravity. The force of gravity. That's why this occurs. So when you are going against gravity, you are going against gravitational force. You feel additional weight. But when you are descending, that's why they said weightlessness. When you are descending, you feel weightless. Okay? You feel this lightheadedness, especially when you are inside an elevator. You feel like say, I want to turn you. You don't know where you did again. Something like that. All right? So let's quickly look at let's leave this complanar force. This is not part of the common questions set in College of Nursing Sciences entrance exam. Both Lami's theory, very, very rare. Okay, let's look at moment. Moment is the turning effect of a force about a point. The turning effect of force about a point. That is moment for you. And moment is very simple. I will make it very easy for you. Okay, moment. Turning what? Effect of a force about a point. Okay, underline force and point. So we have a pivot here, for example, or a pivot. We have a force here. Let's put 20 Newton. Here we have another force. Let's put 18 Newton. All right. So this is the moment. If this presses down, here is going to go up. All right. Here is going to go up, and here is going to what? Come down. All right. So the turning effect of a force about a point. Here is the point. All right. Where we have the fulcrum or the pivot. All right. So the formula of motion is simple. All right. First of all, let's write the formula of moment. Moment is equal to force times the distance, which is perpendicular. Perpendicular distance. All right. Force times perpendicular distance. All right. What is the distance here? If the distance is given, you times this. All right. If they ask you to calculate the moment from here to here, between here and here, what is the distance? Let's say the distance here is let's put 5 meters. Okay. To here. And they say calculate the moment from A to B or from A to O. What do? You do 18 times 5. You get your answer. As easy as that. So if they tell you to calculate all the moments, the moment of the entire system, and maybe here we have also 5 meters as the distance between here and here. What will you do? Just calculate the moment between here and here, and calculate the moment between here and here. Then you add the two. Because the law of moment states that the summation of clockwise motion. Clockwise means ascending, like this one, going up, when it's going up, or when it's going up. Then anti-clockwise is when it's coming down. Is equal to, summation of clockwise is equals anti-clockwise. Anti-clockwise is when it's coming down. Okay, so it means that if you have to calculate the entire moment, the moment of the entire system, you add this side, which is for the clockwise, and you calculate this side and add it with this side, which is for the anti-clockwise. You add them together and get your answer. Say here, the total, we do 18 times 5. plus, put this in bracket. What do we have here? 20 times 5. Put in bracket. All right. You are just going to, what you are just going to do here, you are just going to minus 10. Okay. You minus 10 from 100. Is that not 90? So 90 plus 100 equal to 190. So the entire moment is equal to 190. All right. That's that for that. Entire moment equal to 190. All right. Okay. So let's look at something very vital here. Okay. Let's look at something very vital here, which is known as couple and torque. All right. Couple and torque. Very important. They always repeat questions from there. Couple and torque. This couple and torque is still, let's still leave the moment because it's still under moment. Okay, couple and torque. So for couple and torque, a couple is two equal and opposite forces. Okay, or a couple is two equal and opposite force. For example, let me show you. This is a tap head. Tap where you fetch water. This is the tap head. Okay. So if you want to open this tap so that water will start rushing into your bucket here, what do you do? What do you do? You are going to put your thumb here, this left side, and you put this, your index finger at the right side, right? Then you apply opposite force to loosen it, right? So that equal and opposite force that you are applying on both ends is known as what? Couple. Couple. Okay? Another one again. You try to open your flask, your food flask. The one you call cooler. You apply force on this side at opposite direction. You also use your thumb to apply force at this side, opposite direction. So that is known as equal and opposite force. Couple. Then what is torque? Torque is the circle created by a couple. Torque is the what? The circle created by a couple. Remember, this couple creates a circular rotation. Okay? Or it creates a circular rotation. So that circular rotation created by this couple is known as a torque. All right? That circular rotation created by the couple is known as a torque. And torque is equal to force times distance. All right? Torque is equal to force times distance. Work done. All right? Torque is equal to what? Work done. As simple as A, B, C, D. You are going to see this in your examination. Trust me. So application of the principle of moments is usually applied in lever system in machine. This is one. Also applied in wheel, spanner, door handle. I gave you one tap. You understand? Couple in engine. You know, couple in engine system. All those systems involving rotation, machinery. All right, in machinery and so on and so forth. So if you just understand the principle that I just explained, to know the application is not going to be hard. All right, to know the application is not going to be hard at all, provided you know what I just explained. Understanding the center of gravity of a body. The center of gravity of a body. The center of gravity of a body is that part of the body whereby all the entire force of the body is at the highest. Okay? Where the entire force of the body is maximum. That's the center of gravity of a body. Where the entire weight or force of a body is maximum. Okay? That's known as CG, center of gravity. All right? That's known as center of gravity. For example, if we have a pendulum like this, this is a pendulum bulb. Where is the center of gravity of this pendulum bulb? This is the center of gravity. Close to the what? Close to below the pendulum bulb. That's where you are going to have the center of gravity. Okay? Where the weight of the body acts. Where the force of the body acts. If I drop this pendulum now here, if I drop pendulum bulb now, here, where does the weight act? It's here now. So this is the center of gravity of the pendulum bulb, for example. A human like you, where is your center of gravity? Where does your weight act? Your weight acts towards the lower part, the lower half of your body. That's where your weight usually acts. So that is your center of gravity. Okay. So in women, for example, their center of gravity is located around the lower half of their body. That's why they are always they always store weight in the lower part of their body. Okay, the lower part. But in men, they have their build. Okay, their weight acts on the upper part of their body. We're going to see arm. They look huge. Then their leg becomes so tiny. Most men like that. So you have their weight here, upper center of gravity. Then in women, mostly lower center of gravity, and so on and so forth. All right. Equilibrium of forces. Equilibrium of forces. Equilibrium means balance. Balancing of forces. Balance. Remember, we have physical equilibrium and chemical equilibrium. Chemical equilibrium is in chemistry. We already talked about that. Let's say this is a pivot. We are talking about a physical equilibrium. This is Mr. A sitting, okay, on this place. This is Mr. B sitting on this place. This is a physical equilibrium. All right. So equilibrium is balance. If the weight of Mr. A is 15 Newton, and weight of this Mr. B is also 15 Newton, there's going to be what? A stable equilibrium, right? Yes. So if I drop an object, for example, a cup of water, is going to balance up, right? There's going to be what? A stable equilibrium if I put it on a leveled surface. Okay. But if I put it in a surface that is not level, maybe the surface is slope. Okay. There's going to be an unstable equilibrium. All right. So the force of the body or the weight of the body is going to act on that part that is making it unstable. Or for example, I stand a cone. This is a cone. Okay. Like this. I stand it on this part. What are you going to notice? You are going to notice because the equilibrium is unstable, it's going to fall to the left and to the right. It's not going to balance. If I decide to put this place, I turn it upside down like this. I put the cone like this. What is going to happen? It's going to topple over. All right. That is because there is no equilibrium. There is what we call the unstable equilibrium. All right. Unstable equilibrium. So for us to get a stable equilibrium for this cone now, for example, we are going to have to create the surface in a way that is going to accommodate every part of this, of the cone. Something like this, a curved surface. So when we put the cone is in what? Equilibrium. All right. So we have three types of equilibrium, physical equilibrium majorly. We have stable equilibrium, we have unstable equilibrium. All right. And we have the final one, which is neutral equilibrium. All right. So understanding stable and unstable equilibrium and also neutral equilibrium. The body returns to its original position when slightly displaced. So, for example, understanding the stable equilibrium, when you slightly displace the body, it returns to the original position. For example, this cone now, this is a straight surface, and this cone, because the under is curved, because the under is curved, this is the what? The straight surface. This is, you met the cone like this. All right. You met the cone like this. And when you come, this is the original position of the cone. And you disturb this cone a little. It's going to do like this. And it shakes like this. And you discover that it's going to return back to this original position. All right. So that is for the base of the cone. So this gives us a stable equilibrium. Okay. For example, cone base. All right. Placed in a leveled place. All right. So for unstable equilibrium, here we are now going to see the tip of a cone. All right. We put the tip of a cone like this. We invert it and put it in a level place. The unstable equilibrium is a kind of equilibrium whereby when an object is disturbed slightly, it topples over. It doesn't return to its original position. It's going to change position. All right. It changed a little bit from the normal position that it was in. That's the original position. It just changes a little bit. That's why it's called topple over. Okay. It moves slightly away. It's displaced a little. Like I said, the example is this tip of cone. If you put this tip of cone here now, the position of this cone, for example, if you try to put the tip of cone, it's going to fall. Okay. And when it falls, if you touch it, it's just going to no much difference from the position of the cone. So this is the tip of a cone. The tip of a cone. This one is the example of unstable equilibrium. Therefore, neutral equilibrium is when you disturb a body and the body returns to, or the body attains an entirely new position. It attains entirely a new position. That is what neutral equilibrium. You can see how it started. Stable, you disturb the body, it returns to original position. Unstable, you disturb the body, it topples over. There is just a little displacement in the original position. Then neutral is what? Is when you disturb the body a little, it assumes a new position entirely. So it's when you put a ball on a flat surface. Ball on a flat surface. So this one is an example of neutral equilibrium. So this is a flat surface. We put a ball. When you disturb the ball, what happens? The ball attains a new position. You see it in another position. All right. So that's that for that. It's displaced. All right. So center of gravity usually matters here. Okay. Center of gravity usually matters here. All right. For an equilibrium to be stable, okay, you are going to need a large center of gravity. For it to be unstable, you are going to need a small what? Center of gravity. Okay. Therefore, neutral equilibrium, I think you have no center of gravity at all because it's assumed a new position. All right. So that's that for that. We are understanding static and dynamic friction. Please do not forget to answer the questions found in the notes. Don't forget that. Answer the questions found in the notes.